A thin layer of chromium atoms, only a few atoms thick, forms a self-healing shield that stops stainless steel from turning orange, even after years of exposure to water, salt, and air. Let's dive into the hidden chemistry that This invisible armor is why your kitchen sink stays bright while a rusty nail disappears, and understanding it reshapes how we protect everything from bridges to medical implants. The story begins in the early 20th century, when engineers searched for a metal that could survive the harshest industrial environments without constant repainting. They discovered that adding just a few % of chromium to iron produced a new alloy, stainless steel, that seemed immune to the familiar red rust that devours ordinary steel. But the magic isn't in the bulk metal, it's in a microscopic film that forms spontaneously on the surface. When chromium atoms encounter oxygen, they rearrange into a compact, tightly bound oxide layer called chromium-3 oxide, Cr2O3. This layer is only about 3 nanometers thick, roughly the size of a few dozen atoms stacked together, but it adheres so strongly that it seals the underlying iron from further oxygen and moisture. If the film is scratched, the exposed chromium instantly reacts with the surrounding air, repairing the gap within seconds. This self-repairing behavior is known as passivation, and it's the cornerstone of stainless steel's corrosion resistance. The chemistry of passivation hinges on the concept of oxidation reduction, or redox, reactions. In ordinary steel, iron atoms lose electrons to oxygen, forming iron-3 oxide, Fe2O3, the reddish rust we all recognize. Rust is porous and flaky, allowing water and more oxygen to seep in, accelerating the decay. Chromium, however, prefers to exist in the +3 oxidation state, forming a dense, adherent oxide that blocks further electron transfer. The protective film is electrically insulating, preventing the electrochemical cells that drive corrosion. In essence, chromium turns the surface into a tiny, impermeable barrier, much like a raincoat for the metal. Not all stainless steel is created equal. The alloy's composition determines how well it can form and maintain this passive layer. The minimum chromium content needed for passivation is about 10.5% by weight. Below that, the oxide film is incomplete, and the steel behaves like regular iron. Adding nickel, molybdenum, or other alloying elements tweaks the film's stability and resistance to specific environments. For example, 304 stainless steel contains roughly 18% chromium and 8% nickel, making it versatile for kitchen appliances and food processing. Meanwhile, 316 stainless steel adds about 2 to 3% molybdenum, which dramatically improves resistance to chlorides, why it's the go-to material for marine hardware and surgical instruments. The presence of chlorides is a crucial weakness in the stainless steel story. In coastal areas or inside swimming pools, chloride ions can penetrate the chromium oxide film, disrupting its continuity. This process, called pitting corrosion, creates tiny, localized holes that can grow rapidly, eventually leading to structural failure. Engineers combat this by selecting higher molybdenum alloys, applying protective coatings, or designing components to avoid crevices where chlorides can accumulate. Even the most resistant stainless steel can succumb if the environment is aggressive enough. Beyond composition, the manufacturing process influences the alloy's performance. Cold working, stretching or bending the metal at low temperatures, can increase tensile strength but also introduce microscopic strains that affect the oxide layer's uniformity. Conversely, annealing, a heat treatment that relieves stress, helps the chromium atoms migrate to the surface, thickening the passive film. That's why many stainless steel products undergo a final annealing step before shipping. The story of stainless steel isn't just about chemistry, it's also about economics and sustainability. The alloy's durability reduces the need for frequent replacements, saving resources over a product's lifetime. However, extracting chromium from ore is energy-intensive and generates waste. Recycling stainless steel mitigates these impacts, as the alloy retains its corrosion-resistant properties even after multiple melt cycles. In fact, over 70% of stainless steel produced today comes from recycled scrap, making it one of the most recycled materials on the planet. To illustrate the real-world impact, consider the iconic Eiffel Tower. Originally painted to protect its iron structure from rust, the tower required regular maintenance, a costly and labor-intensive process. In 1985, engineers replaced large sections of its iron with stainless steel components, dramatically extending the tower's lifespan and cutting maintenance costs by half. Similarly, modern skyscrapers use stainless steel reinforcement bars, or rebar, within concrete cores. The rebar's corrosion resistance prevents the cracking and spalling that would otherwise compromise a building's integrity after just a few decades. Medical implants provide another striking example. Hip replacements, stents, and surgical tools often rely on 316L stainless steel, a low-carbon variant that resists pitting in the body's chloride-rich environment. The alloy's biocompatibility ensures that the implant does not trigger adverse immune responses, while its corrosion resistance guarantees that metal ions won't leach into surrounding tissue, a vital safety feature for long-term implants. Even everyday items we take for granted showcase the hidden chemistry. The sleek stainless steel of a kitchen sink resists staining from acidic foods because the passive film quickly reforms after each wash. The polished cutlery we use for dinner maintains its luster because the chromium oxide layer prevents iron from oxidizing, even after repeated exposure to salt and moisture. And the stainless steel frame of a bicycle can endure years of rain, sweat, and road grime without turning brown, thanks to that same nanometer-thin shield. But the alloy isn't invincible. Improper cleaning agents, such as chlorine bleach, can erode the passive layer, especially if left on the surface for extended periods. Mechanical damage, deep scratches or abrasive polishing, can expose raw iron, allowing rust to initiate. That's why manufacturers recommend using non-chlorine cleaners and soft cloths for routine maintenance. Looking ahead, researchers are pushing the boundaries of corrosion resistance even further. By nanoengineering the surface, they aim to create superhydrophobic coatings that repel water entirely, reducing the need for chromium altogether. Some teams are experimenting with alloying elements like titanium or tantalum, which form even more stable oxides. Others are exploring self-healing polymers that release corrosion inhibitors when the metal is damaged. These innovations could lead to next-generation alloys that are lighter, stronger, and even more sustainable. In the end, the humble stainless steel spoon in your drawer embodies a profound interplay of atomic chemistry, engineering decisions, and environmental considerations. Its ability to stay rust-free stems from a few percent of chromium rearranging into an invisible, self-repairing armor that shields the iron beneath. This tiny film, only a few atoms thick, is a testament to how a subtle change at the molecular level can transform entire industries, from architecture to medicine. The next time you see a gleaming stainless steel surface, remember that the brilliance you admire is not just a finish, it's a dynamic, protective skin that has been quietly battling corrosion for over a century, keeping our world cleaner, safer, and more durable.